Hi everyone! So towards the end of Calculus 1 is where you learn all about area and value. And I actually find this fascinating that you can find the area of an irregular figure or the volume of an irregular three-dimensional figure all using calculus. It is excellent. So in this problem, we are going to find the volume of a solid whose base is bounded by the graphs of this linear function, y equals x plus 1, and this quadratic function, y equals x squared minus 1, with square cross-sections that are taken perpendicular to the x-axis. So let's first think about this visually. I'm going to sketch an x and a y axis, and then I'm going to graph the linear function y equals x plus 1. That would have a y-intercept of 1 and a slope of 1, so it looks something like this. And then for the parabola y equals x squared minus 1, well, I know that's going to be a parabola shifted down 1, so I know it will go through the y-axis right about here. But before I graph it, just to get a little more accurate graph, I'm going to find where these two functions intersect. To do that, I am going to set x plus 1 equal to x squared minus 1. We will also need to know these points of intersection later when we go to write the integral. So that's why it's important when you're solving this by hand to actually find those intersection values. So I will subtract the x over and subtract the 1 over to get this quadratic function that I'm going to solve by factoring. So I'll go ahead and factor this to get intersection values of 2 and negative 1. So I know these functions intersect at the x value of negative 1, which would occur right there. And when I go to graph the parabola then, I know that is one of the intersection points. And then at the x value of 2. So that's going to be right along here. And if I plug in 2 to the function, I can see that the y value would be 3. So that's going to be up here right there. So that, sketching that is going to help me see that this is the base. So the base is going to be this region right there in between those two graphs. Now that's going to be the base, but the cross sections are going to be squares. So when I think about them, when I think about those squares that are perpendicular to the x-axis, here is the base of the square right there in the region. And then think about the square coming out three-dimensionally towards you. So as best you can, envision that red square coming out of the screen. Okay, now to find this, we would need to set up an integral in order to find the value. And the reason we're doing that is because we are going to sum up an infinite amount of squares between the first x value and then the last x value. And to do that, we need to define those x values, which we solved right down here. So we're going to add up an infinite amount of these red squares from an x value of negative 1 to an x value of 2. And again, we found those algebraically. Now we need to write the area of each square. So the area of a square is going to be, the area of a square is going to be one side of the square times itself, side times side, or side squared. So to get one side of this red square, we would need to take the top function minus the bottom function, or the linear function in pink, minus the quadratic function in blue. And that's going to be one of the sides. So once again, let me write that out. So it'd be x plus 1, the linear function, minus the quadratic function, x squared minus 1. That's going to be one side of the red square. And then we know that the area of a square is that side squared. And don't forget your dx after your integral. That's going to represent the little width of that square. So this is how we would find the volume of an infinite amount of squares added up between the x values of negative 1 and 2. From here, if you're solving this by hand, it's just a whole lot of algebra. So I'm going to do my algebra off to the side. And there is the simplified polynomial once I multiply everything out. And I'm going to use this right here to put back into my integral, which is up here. There we have it. Now it's time to integrate. The best part, find the antiderivative of this polynomial. So here I have used the power rule for each of these terms. I added one to the exponent and divided, and now I'm going to evaluate this between the x values of -1 and 2. Just a reminder, when solving integrals, I'm going to plug in the top value of 2 into this polynomial and then subtract what I get when I plug in -1 into this polynomial. Now for a bit more arithmetic. Almost there. Time to get common denominators. And there we have it, 81/10 or 8.1. Again, that is going to be the volume of this solid that has an infinite amount of squares from -1 to +2. And that's it. That's how you would find the volume of a solid when you're given a base and you have cross sections. Now, sometimes these cross sections may not be squares. If that is the case, just use the area of that shape in the place of the area of the square, and just like that, you'll have it. And that's how you would use calculus to find the volume of a three-dimensional figure using cross sections. I hope you found this video helpful. If you did, make sure to give it a like and subscribe if you haven't already, so you can see future calculus videos as they are posted to help you all in your calculus learning. Have a great day, everyone, and we'll see you in the next video. Bye.